Quantum communications, basics and future directions. Quantum communications, basics and future directions. In the digital age where information is the new currency, secure communication channels are crucial for businesses, governments, and individuals. The traditional cryptographic methods based on mathematical calculations are no longer foolproof against advanced hacking techniques. Quantum communications, on the other hand, offer a solution based on the principles of quantum mechanics, which is the study of matter and energy at the subatomic level. Quantum communications use photons, which are the smallest particles of light, to transmit information. The two fundamental principles of quantum mechanics that underpin quantum communications are both superposition and entanglement. Superposition is the concept that an object can exist in more than one state simultaneously. In the case of photons, they can exist in multiple states of polarization, which determines the direction of the electric field in the light wave. For example, a photon can have horizontal polarization, vertical polarization, or any angle in between. By exploiting this property, quantum communication can encode information in multiple states, which can only be decoded by the receiver who has the key to decode it. Entanglement, on the other hand, refers to the correlation between two or more particles that can exist even when they are physically separated. When two photons are entangled, the state of one photon is instantly determined by the state of the other photon, regardless of the distance between them. This phenomenon is commonly referred to as spooky action at a distance, and it has been confirmed in numerous experiments. Using these two principles, quantum communication can achieve a level of security that is impossible with traditional communication channels. One of the early applications of quantum communications is called quantum key distribution, QKD. This technique uses the principles of quantum mechanics to establish a secure key between two parties that can be used to encrypt and decrypt messages. The key is generated by the sender using a stream of photons, with each photon carrying a random polarization state. The receiver uses another stray of photons to measure the polarization state of the photons, which forms the key. Since the act of measuring the photons changes their polarization states, this ensures that any attempt to intercept the key would be detected. QKD has already been successfully demonstrated in laboratories, and commercial products are available for organizations that require the highest level of security for their communication channels. However, the cost and complexity of implementing QKD have limited its adoption outside of niche markets. One of the challenges of quantum communications is the distance over which information can be transmitted. Photons can lose their quantum state when they interact with matter, such as air molecules or optical fibers. Additionally, the no-cloning theorem of quantum mechanics states that it is physically impossible to duplicate a quantum state. This means that quantum information cannot be amplified, making it harder to transmit over long distances. The current state-of-the-art for long-distance quantum communication is based on a technique called quantum repeaters. Quantum repeaters use intermediate nodes to extend the distance that quantum information can be transmitted. Rather than transmitting the photons directly between the sender and the receiver, they are relayed through intermediate nodes that store and retransmit the quantum information. This allows information to be transmitted over much longer distances and with higher fidelity. Another area of active research in quantum communications is quantum teleportation. While it sounds like science fiction, quantum teleportation is a real phenomenon predicted by quantum mechanics. 2. Atom teleportation uses entanglement to transfer the state of one particle to another particle. The process involves three particles. The sender, Alice, has a particle that she wants to teleport to. The receiver, Bob, and they share an entangled particle. Alice performs a measurement on the entangled particle and the particle to be teleported, sending the result of the measurement to Bob. Bob T. Hen performs a transformation on his entangled particle based on the measurement result, which causes it to become identical to the particle that Alice wanted to teleport. Quantum communications hold promise for a wide range of applications, including secure online banking, military communications, and even long-distance space communication. However, there are still why technical challenges that need to be solved before quantum communications can become a mainstream technology. Additionally, quantum communications must develop alongside quantum computing, as ADVA. This in one field can potentially undermine the security of the other. One potential application of quantum communications is in the field of quantum computing. Quantum computers, which are still in their early stages of development, use quantum bits, qubits, to perform calculations that are beyond the capabilities of classical computers. However, the same properties of superposition and entanglement that make quantum computing possible also make it vulnerable to attack by hackers. Quantum communication can provide a solution to this problem by allowing quantum computers to communicate securely with each other and with other devices. By using quantum communication to transmit T inputs and outputs of a quantum computer, it is possible to ensure that the quantum state of the computer is not compromised during the computation. This is known as blind quantum computation, and has been demonstrated in several experiments. Another potential application of quantum communications is in the field of quantum sensors. Quantum sensors use the principles of quantum mechanics to measure physical quantities such as magnetic phi LBS or temperature with higher precision than classical sensors. For example, a quantum magnetometer can detect tiny magnetic fields that are impossible to measure with traditional sensors. However, quantum sensors are also vulnerable to interference from external sources, which can cause them to lose their quantum state and reduce their accuracy. By using quantum communication to transmit the information from the quantum sensor, it is possible to protect against outside interference and ensure that the sensor provides accurate measurements. Possible application of quantum sensors is in the field of medical imaging, where high-precision sensors could be used to detect early-stage cancer or other diseases. China has also made significant advances in quantum communications, including launching a quantum satellite in 2016 that was used to transmit information